When severe floodwaters overwhelm a Thai municipality, volunteer engineers deploy directly into the disaster zone to assess the structural and electrical safety of the remaining buildings. The physical disruption is massive. Whole districts are submerged in highly conductive mud, roads are washed out, and infrastructure is completely compromised. Parallel to this physical chaos is a strict administrative reality. The Thai Council of Engineers requires its members to accumulate a rigid sum of Continuing Professional Development, or CPD, units. CPD is a mandatory system of education and fieldwork credits required to advance an engineering license from the associate level to the professional or senior tiers. Starting in 2025, that requirement locks in at exactly 150 units. That specific number is dictated by international agreements. Accumulating 150 units is the exact threshold required to maintain standing in the Washington Accord and hold the title of Apex Engineer, a recognized international standard that allows for cross-border professional mobility. Executing rapid field diagnostics in a flood zone and calculating bureaucratic CPD multipliers in a portal are two halves of the exact same professional survival requirement. Upon entering a compromised area, an engineer's workflow relies on a centralized assessment app. They drop a precise GPS pin, upload photographic evidence, and log the specific visual damage of the structure. The software processes this data into a standardized triage map, assigning a binary safety classification of red, yellow, or green to every surveyed building. This creates immediate friction in the field. Residents facing ruined homes frequently demand that the engineer provide immediate, on-the-spot financial estimates for repair costs. This diagram illustrates how the app's architecture explicitly prevents that. It incorporates a hard liability wall. The system deliberately prohibits engineers from inputting cost data, isolating them from financial disputes. The engineer's sole mandate is structural and electrical safety. Translating that physical damage into financial compensation remains the exclusive domain of municipal authorities. As floodwaters recede, like in the recent Chiang Rai deployments, the most immediate threat shifts from drowning to electrocution. The primary diagnostic target inside any residential building is the main electrical consumer unit, which is typically found inundated with thick, conductive mud. This creates a macro dependency problem. The provincial utility company will refuse to reconnect power to an entire street until every single individual consumer unit on that block is cleared and certified safe. Engineers must manually flush the mud from the panels and perform insulation testing using a megometer. A megometer is a specialized instrument used to measure the electrical resistance of insulators. Only a passing resistance value allows the unit to be cleared. Digital data entry is useless without this physical intervention. The municipal grid cannot function until the hardware is manually secured. Once the electrical risk is neutralized, the triage shifts to the structural integrity of the walls and foundation. Surface cracks in concrete and masonry dictate the hidden failure mode of the building. The orientation of a diagonal fracture is entirely deterministic. It follows strict geometric rules. Here is how you read the geometry. If you draw a perpendicular vector line outward from a diagonal crack and point it downward, that line will aim directly at the failing foundation element. In one field case study of a 3-story building, this exact vector analysis pointed to a specific footer, revealing severe differential settlement on one side of the structure. The mechanical cause was hidden underground. A massive, unrecorded volume of sandfill had been dumped over a short 6-meter pile to level a parking area, completely overloading its bearing capacity and crushing it downward. The surface-level architectural cracks act as a direct, readable map of these hidden subsurface failures. The third major failure category occurs outside the building entirely: geotechnical slips along community canal banks. The physical trigger is often the rapid drawdown of floodwater, usually through aggressive pumping. This instantly removes hydrostatic pressure, the outward force exerted by the resting fluid, causing the heavy, saturated soil to flow outward into the empty canal. The primary visual warning sign is the sudden appearance of longitudinal tension cracks on the asphalt road surface, running perfectly parallel to the waterway. This diagram shows the geometric rule for emergency remediation. The exact horizontal distance from the tension crack to the canal bank represents the depth of the impending slip circle in the soil below. This surface measurement dictates the absolute minimum length required for remedial timber piling. If the crack is 4 meters from the edge, the timber piles anchoring the sliding soil must be driven significantly deeper than 4 meters to intersect the slip circle. An engineer's core value during triage lies in translating chaotic physical symptoms into precise mathematical safety countermeasures. All of this grueling disaster volunteer work must eventually be translated into the mandatory CPD units required for a professional or senior engineering license upgrade. The Council's core algorithm multiplies a base metric by a weighting factor to yield total CPD units. For disaster volunteer work under CSR, the base metric is actual hours worked, receiving a 2.0 weighting factor. 24 hours of field triage yields exactly 48 CPD units. This aggressive multiplier contrasts sharply with Category 508, project management, which mathematically ignores actual hours worked. The project management algorithm uses a fixed base of 5 units per project, multiplied by a 2.0 weight. This creates a hard cap of 10 maximum units per project, regardless of whether you invest 50 hours or 10,000 hours. The Council's algorithm evaluates administrative project responsibility vastly differently than physical volunteer labor, requiring engineers to be strategic about how they log their time. This logic also applies to Category 101, formal education, determining how academic degrees translate into points. For a master's degree, the calculation takes the number of registered credits, multiplies them by 15 hours, and then applies a weighting factor. This graphic illustrates the split. Engineering degrees receive a full 1.0 weight. Non-engineering degrees, like business or law, receive half the value with a 0.5 weight. This logic carries over to Category 102, professional training and seminars. This chart shows the distinction in the calculation. Simple attendance yields a 1.0 weight based on hours. Passing a concluding exam instantly doubles that weight to 2.0. The overarching CPD algorithm is designed to mathematically incentivize verifiable competency over mere attendance. The final administrative hurdle is successfully inputting this calculated data into the Council of Engineers portal. There is one exception to manual entry. Activities hosted directly by a core organizational network, an Ongon Mekai, will sync to an engineer's profile automatically. For all other activities, strict authentication applies. Logging in requires possessing both your national ID number and your council member number, followed by OTP verification. Once inside, the UI is specific. You select Bantuk Kanan CPD to manually record points and Dirtsop Kanan My CPD to audit your current progress toward the 150-unit goal. The 150-unit CPD standard serves as the ultimate verifiable ledger. It mathematically proves that a Thai engineer possesses both the diagnostic rigor to assess a flooded municipal grid and the continuous technical evolution required to hold international APEX status.